I think we're live. Let me just check. Yeah, okay, we're live. Okay. So hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the honor of having Dr. Pablo Santos-Sanz, a researcher at the Instituto of Astrophysics of Andalucía. Dr. Santos-Sanz is a specialist in small bodies of the solar system, such as asteroids, comets, and trans-Neptunian objects, which we call TNOs for short, and is the co-discoverer of more than 200 asteroids and TNOs. He's currently leading several Centaur and TNO research programs with the James Webb Space Telescope. Dr. Santos' main area of research are small bodies of the solar system, photometric techniques, and stellar occultations using different telescopes on the ground and in space, and the detection of flashes of impact of bodies against the moon. Dr. Santos-Sanz, thank you so much for being so kind and having accepted to give us a webinar talk today on such interesting topics. The floor is yours.
Thank you very much, Tasia. It's my honor and my pleasure to be here today to talk about trans-Neptunian objects and how to unveil in the trans-Neptunian belt using thermal data and also stellar occultations. Okay. I want just start talking about where are the objects in which I'm interested. These are the trans-Neptunian objects, or TNOs. As Tasia said, that they are objects that have semi-major axis larger than the semi-major axis of the Neptune orbit, and include also dwarf planets like Pluto, Eris, Haumea, Makemake, and other more dwarf planets that are not classified currently as dwarf planet, but they are because of the size and because of the hydrostatic equilibrium. I'm also interested in the centaurs, which are related with the trans-Neptunian object and are transition objects that has orbit, semi-major axis, orbit with semi-major axis between Jupiter and Neptune. We know up to date around 3,500 of these objects, and the important thing is that these objects are the leftovers of the formation of the outer solar system. In some sense, we can say that these objects are a kind of time capsules because they have retained the information on the origin and evolution of the solar system, in particular of the outer solar system. So we can obtain many information about this origin and evolution, and also information about another extrasolar systems. Well, what we know about trans-Neptunian objects and centaurs? Well, we know we have information, but not for many, because if we take into account that we know about 4,000 of these objects, we have information, of course, of around 500, rotational light curve 150, and you have here all the things that we know. Taking into account this around 4,000, well, there is a lot of things to learn about these objects. I'm very interested in these physical properties that are in blue in the slide, that are the sizes, albedos, thermophysical properties, mass densities, 3D shapes, the presence or not of rings, atmospheres, and topographic details. We can obtain this information in blue using thermal data and also using stellar occultations. Well, what do we do with the thermal data? If we have thermal data of one of these objects, we apply a thermal model. I'm not going to stay in this slide a lot. Basically, this is the easy way to obtain information from the thermal data. Basically, we assume that the object is spherical, and we did another assumption. The important thing is that fitting the data, fitting the spectral energy distribution that we obtain from the thermal data, we can obtain diameters, albedos, and a factor called beaming factor that includes the information about the thermal inertia, the rotational period, and also the surface roughness. Well, we can do the model more complex, and then we will have what is called a thermophysical model. From a thermophysical model, we can obtain information about sizes, albedos, and also the thermal inertia and the surface roughness. So we can obtain more information on the thermophysical properties of the objects. The problem is that to apply a thermophysical model, we need more information on the object. Typically, we need to have information about the three-dimensional shape, also the rotational period, the position of the rotation axis, and then with this we can run this thermophysical model. Here, well, you have some examples, and the thermal inertia equation that depends on the thermal conductivity, the density, and the heat capacity of the body. What about thermal observations of trans-Neptunian objects and centaurs? Well, the thermal emission from TNOs and centaurs, this is the typical temperature of a TNO, that is between 20 from 20 to 50 kelvins, and for centaurs is 70 kelvins. The thermal emission has the maximum between 50 and 160 microns. This means that, okay, these wavelengths are only accessible from the space. The peak of the thermal emission of TNOs and centaurs only can be observed from space. From the ground, we also can observe the thermal emission of these objects. In fact, we have data from radio telescope on Earth, like IRAN, GCMT, and also ALMA in the last times. And we can also obtain, of course, we are not in the peak of the thermal emission, what are useful data. From Spitzer, we obtain around 45 observation from 45 of these objects, and for the brightest centaurs as well with WISE. Well, the observatory, the space mission that obtained more data about the thermal emission of this object was Herschel Space Observatory. Within the key open time program called TNOs are Curl, a survey of the trans-Neptunian region. From this program, we obtain the thermal emission of 140 of these objects. Well, with this thermal data, applying thermal or thermophysical model, we can then obtain sizes, albedos, thermal properties, and if the object is a binary or multiple object, we can obtain also densities. What is the problem? Well, the problem is that the typical errors are around 10% in diameters and around 20% in albedos. These are large errors, and also, well, what we obtain is that diameters and albedos are model dependent. Here in this slide, you have the main result of this TNO-SARCU project using Herschel Space Observatory data of TNOs and centaurs, together with ancillary Spitzer data. You can see here, well, with these colors, the different albedo objects and also different sizes, which are the main result from this project: sizes, albedos, and also thermal properties. Just to summarize what we know, we have thermal measurements for about 180 TNOs and centaurs using Herschel and other facilities. We have sizes, albedos, and this beaming factor, if we apply this thermal model that I was talking about in one of the previous slides, if we have measured for 11 big objects larger than 900 kilometers. We have objects very dark with albedos between 3 and 4%, and also objects very bright, albedos between 50 and 90. The mean albedo is around 10%. This means that are really dark objects, most of them. And also we have this mean thermal inertia that is 2.5. This is really a small thermal inertia, which means that the ices in the surface of this object are not compact ices, are ices, very porous ices. Well, here in this table you have the thermal inertias we derive for these objects. Also here you have a plot, a color albedo plot, where you can see clearly two different groups. This in red are objects red in color and with high albedo, higher than the mean. And the other group is this blue that are bluer color and also with a small albedo. Probably this is related with different origin for these groups. Well, from thermal data, of course, as we have the sizes, we can obtain volumes. And if we know the masses, this is typically known for binary or multiple objects, we can obtain densities. In this table are the densities derived from thermal measurements. I have put here in red some outliers. The table is sorted from the biggest to the smallest objects. So, well, this is for WC19 is really a high density. So this is probably due to a problem with the thermal or thermophysical model, and we derive finally not realistic density. The same for this object for Borasisi. Well, it's also possible to obtain thermal data with James Webb. In this case, using mid-infrared, and we can obtain this thermal emission using the mirror instrument at between 18 and 25 microns. And these data are complementary to the data that we obtain with Spitzer, Herschel, and ALMA. This data can be important because can resolve ambiguities of thermophysical models and also can help to constrain the thermal inertias and the roughness. Also, well, if we detect thermal excesses at this shortest wavelength, these excesses can be due to hotter terrains. This means low albedo areas, or to the hotter terrains in the surface of the object. Maybe can be due to darker satellites. Well, there are at least there are 3 objects that will be observed soon. Soon, I mean in this cycle 1 of WST, within a GTO using this MIRI imaging, and these are Makemake, Varuna, and Haumea that will be observed at these MIRI wavelengths, with a rotational coverage. This means that for some of these objects, we will obtain the rotational light curve, in particular for Varuna, and we could compare this light curve with light curve that we obtain, for example, with Herschel Space Telescope. If in the case of Varuna, well, the light curve obtained using Herschel Space Telescope, Herschel Space Observatory, has some things that we can't explain. We don't know what happened with this light curve. So probably with this James Webb data, we can understand what is happening with Haumea. Well, some years ago, also I asked me the question if it would be possible to obtain thermal data of trans-Neptunian and centaurs using the square kilometer array. And yes, trying to ask this question, well, first, if we take a look to the bands, probably the only bands at which we can detect this thermal emission is the bands at the highest frequencies, which mean the smallest wavelengths. Typically are band 5 and band 6 of SKA. These are in wavelengths, well, from 0.7 to 6.5 centimeters. So, well, the question is, can we measure this with SK or not? SK1 mid, well, SK1 is the first phase of this project. That there will be two phases. First SK1, and then will be SK2 that will arrive later in time. So, well, we can estimate if we have like in this slide for the TNO Salacia, if we have information for different thermal wavelengths. I can fit here the thermophysical model. Then, well, in red, for example, here I have the data from Spitzer. In black are the data from Herschel, the Herschel PAX. In green, Herschel Spire, and in blue are the data from ALMA. Well, we can extrapolate this fit to the wavelengths of SKA, and if we do that, well, we obtain that at least for the shortest wavelength, we can detect the thermal emission of Salacia. Well, you can see that this is extremely low thermal emission because these are micro-Janskis. Usually in Herschel, we work using milli-Janskis for TNOs, but here we are talking about micro-Janskis, but it's possible. I did the same for the biggest object. Around, I think I did this for around 30 objects. Well, again, the table is sorted from biggest to smallest object, and for this SK1 mid wavelengths, in green are the objects for which would be possible to detect this thermal emission using SK1 mid SK. Well, you can see here also centaurs, Cariclo, Vienor, Chiron. Then the conclusions are that, yes, it will be possible to detect the thermal emission for most of the TNOs larger than 300 kilometers, and also for the largest centaurs. With the second phase of the project, with SK2 mid, that will be around 10 times more sensitive, it will be possible to detect the thermal emission of different wavelengths for all the known TNOs and centaurs. This is interesting because, okay, if we are using centimeter wavelengths, we can sound the subsurface of the object. So we can obtain information using SK. Using ALMA as well, we can obtain information of the subsurfaces of this object. But if you use SK, we can obtain information of more centimeters inside the surface of the object. So it's something interesting that, okay, perhaps we can obtain this information from other projects that observe a field of view where a TNO or centaur is. I move to the other technique that I won't talk about this afternoon, that are the stellar occultation technique. Well, I know that here connected are many people working on stellar occultations. So, but for people that don't know, the stellar occultation technique is a really very powerful technique. The really difficult thing is predict when one of these objects pass in front of a star. But if we predict and observe at the end, we can see here the star, the body, and then observers here on Earth in the shadow path. We can obtain very accurate diameters, albedos, and 3D shapes, also densities. If we have the mass of the object, we can detect and characterize atmospheres, rings, satellites, also topographic features. We can improve the orbit of the object. Also, we can obtain information about the occulted star. Well, this is an example of one of these stellar occultation. In the right, you have with the circle and the zero, you have the star that is occulted, and in the left panel, you have the occultation. You have how the flags of the star and of the body drop close to zero during the occultation when the star disappears. Well, this is nice, but there are really problems to predict a stellar occultation by a TNO or a Centaur. The first problem is that this object has a really small apparent size in the sky. For instance, Eris, that is one of the dwarf planets, has only 33 milliards in size. Well, this is mainly for European people, but this is about around €1 coin seen at 140 kilometers. It's really small. But we are interested in objects that are even smaller than this one, object with 10 milliards in size, in apparent size. Well, so for TNOs and Centaurs, there are a few challenges that we have to solve in order to predict one of these stellar occultation. First, as I said, are the small apparent sizes. Also, the large uncertainties in the orbits. We have observed only a short arc of the orbit of the TNO and of the Centaur. This means that well, the orbital elements has large uncertainties. This is well, it's not good in order to know when will be exactly the object in the future. Also, we have the uncertainties in the position of the occulted star. This is partially solved with Gaia, with the Gaia catalogs. And to obtain a successful prediction, we need know the object's orbit and its ephemeris. We need to know the approximate size of the object. Also, to have an accurate catalog with the position and the magnitude of the stars near the occultation path. And well, last but not least, we need to know observers, potential observers in the shadow path, in the predicted shadow path. Well, this is a experimental, I mean, rule. We need at least 15 observers. This is from our experience in all the stellar occultations that we predict and observe. We need at least 15 observers to obtain a multi-core occultation. I call multi-core occultation this that is observed from at least more than two sites separated. So we can obtain more than two cores. Well, in spite of this challenge situation, we have predicted and observed around 140 occultations by 42 TNOs and 9 Centaurs. So well, the point is that here is that only around 20 of these are multi-core. This means that have been observed from more than two sites, well separated in the shadow path, within the shadow path, below the shadow path. The good thing with the stellar occultation is that the typical errors in diameters and albedo could be around 1 to 2%. If we remember from the thermal models and thermal data, this was around 10 and 20 for diameters and albedos. So we can obtain really, really accurate diameters and albedo sizes and albedos. Well, this is the first stellar occultation by a TNO. Well, these numbers, I forget, are excluding Pluto and Charon system. And the first TNO, excluding Pluto itself, was observed in 2009. And the last one was observed just last night, was an occultation by this TNO 2010 TA5053. And as I said, only for around 20 of these objects we have multi-core occultation. And typically for this object we have obtained diameters and albedo with high accuracy. And for a few of them, densities, also 3D shapes, rings, satellites, atmospheres, and also topographic details that we are starting to characterize in these objects. Well, now I want to talk about a few relevant or outstanding occultations. The first one is the first detected by the team which I form part. That was the occultation by Eris in 2010, the dwarf planet Eris. From this occultation, we obtained the spherical shape. This is the diameter, also the density and extremely high albedo. You can see here that is close to 100%. Well, we didn't detect atmosphere. And the explanation of this extremely high albedo, we think that is due to a collapsed atmosphere that sublimated near the perihelion of Eris. Well, the time of the occultation, Eris was at around 100 astronomical units. So it's expected that the atmosphere can be collapsed and can explain this very, very bright surface. Well, another relevant occultation was the occultation by Makemake, another dwarf planet. Also, we obtained the projected shape that was not circular in this case, and also the albedo of 77% that is in between the Eris albedo that we have seen that it was really very, very, very large, and the Pluto albedo as well. The density that is smaller than the Eris, that, well, this looks like reasonable because it's smaller than Eris. Also, well, we probably detected in this occultation a local atmosphere. This means that parts of it are collapses and other are sublimated in different parts of the body, depending of the probably of the temperature and probably of the color and albedo of different parts of the surface of Makemake. Another really important occultation that well, many people connected, listen the talk know, are the occultation by Caiclo in 2013. Well, these are real images, data of one of these occultation. Well, how many times does the star disappear? Well, I can count at least this 1, 2, and 3. So 2 very short disappearance and 1 large one, long one. So what we are seeing here is this one. We are seeing the rings, detecting the rings of Caiclo and the body itself. You can see here, well, these are the short drops, and this is the big one due to the main body, to Caiclo itself. You can see that, well, there are two rings. This is important because this is the first time that a ring system was detected around a non-planetary body in our solar system. Chariclo itself is around 250 kilometers, and we detected two narrow and dense and very dense rings at around 400 kilometers, separated by around 9 kilometers. Well, you can see here these secondary drops in green that allow to fit the rings around Chariclo. Well, this is a nice animation prepared by Lucie Maquet, when you can see very clear the light curve I showed you and the occultation. Well, the occultation by the rings, then by the main body, and again by the other side of the ring. Nice, really nice. Well, we continue with another really relevant stellar occultation, that is the occultation by the dwarf planet Haumea. We obtain a 3D shape. One of the axis is close to the size of Pluto. This was a really surprise. We also obtain the diameter, the density, and also we discover a narrow and dense equatorial ring at around 2,287 kilometers. And well, I forget to say that the rings of Chariclo are in a spin mean motion resonance 3-1. This means that the one particle in the ring, when complete one revolution, the body has complete 3 revolutions. In this case, Chariclo, but now for Haumea is the same. One particle in the ring complete 1 revolution, and at the same time, the body Haumea, that is rotating at around 4 hours, complete 3 revolutions. Well, taking into account the 3D shape that we obtain, Haumea cannot be a homogeneous ellipsoid in hydrostatic equilibrium for the rotation period of Haumea. Here you can see the different light curve of the occultation, and then how they fit to this ring. Well, this is another animation of this this ring around Haumea, just to have a feeling of the size of the object, the shape, and the distance of the ring. The animation, of course, is based on the result obtained from the occultation. Well, just to summarize the Haumea results, Haumea is larger than previously thought. The density is lower, the surface is less reflective, and as I said, the 3D shape and density from the occultation are incompatible with hydrostatic equilibrium. Well, this means that we need another physics to explain the shape, the 3D shape of Haumea, like maybe granular physics, or maybe the body is differentiated. This is good because this open the way to obtain information about the interior of these bodies. Well, a byproduct is that the definition of dwarf planet, at least the hydrostatic equilibrium condition, should be revised. Well, this is what I like to call the ring revolution. Well, we know that all the giant planets have rings: Jupiter, Neptune, Uranus, Saturn. Then in 2013, we discovered the ring around Chariclo, these 2 rings. In 2015, I forget to say, but we also suspect that Chiron, that is another centaur, has also rings. 2017, around Haumea. And well, what I predict in the next years is that we will discover more and more objects with rings around. This opened the possibility to study what happened with the rings. What's the origin of these rings? Well, in our case, for TNOs or Centaur, how this object obtain the rings, and what is the lifetime of these objects? There are a few theoretical works about the rings around these objects, in particular around Chariclo and Haumea. One of them is by Bruno Sicardi. Two very nice work, 2019, 2020. They discovered that non-axisymmetric bodies produce a strong resonances between the spin of the object and the mean motion of rings particle. These resonances, well, can explain how the rings are formed. If there is this material inside this co-rotation radius, inside this, the co-rotation radius is this radius in which a particle rotates at the same time that the central body. Then, well, material inside migrates onto the body, and outside is pushed outside the 1-2 resonance. And well, this can explain why these rings are at this 1-3 spin mean motion resonance for Haumea and for Chariclo at least. Well, there are also a strong effort to characterize these rings using observational data. This paper from Bruno Morgado of last year so use data of many occultations to characterize the rings, the opacity, the W shape structure detected in the main ring, that is C1R, also the eccentricity and more things. Here are some of the latest published results on occultation. I'm not going to stay a lot in each of these slides. This is 2002 TC302 from 2022. Also for multi-core occultation by the Centaur 2002 GC32. Again, we obtain for some bodies that the shape, the 3D shape we obtain is inconsistent with a homogeneous body in hydrostatic equilibrium. This year, we also published the result of these two stellar occultation by two trans-Neptunian objects. We don't see rings, we don't see atmosphere for these bodies, but well, we characterize, for instance, for 2003 VS2, the 3D shape and other very interesting physical properties. The last published paper was the paper on the occultation by the Centaur Bayenor. This paper was accepted last week. Well, the size we obtained, the equivalent diameter in area equivalent diameter is around 30 kilometers smaller than the thermal. Well, this is weird. This is the feed. You can see that the cores are not allineated. But well, taking into account if this is real, that the cores are like this, and this is not a problem on the teaming, for instance. If this is true, well, we can fit also with a contact binary. And this is the first example of what I want to talk also about in this talk. To fit this contact binary, we need a constraint on the size, on the equivalent size of the object. And we obtain this constraint from thermal data. From the thermal, we know that the equivalent diameter for Bayenor is 181. So using this constraint, we can fit using these cores, and we can fit this binary. This is really interesting because it can explain, well, some things that cannot be explained by this simple elliptical fit. And of course, well, the equivalent diameter of the two bodies is constrained using this thermal data, thermal result. There are other papers about the stellar occultation by these bodies in preparation or submit. Some of them are submitted, some are close to be submitted or in preparation. And another question is that is really interesting is if it's possible to observe this kind of stellar occultations from space, stellar occultation by these objects. Well, the answer is yes. The first one was observed by the satellite CHEOPS in June 2020, and was published just this year in this paper by Bruno Morgado et al. And well, you can see here the prediction. In blue is the path, the shadow path. In red, you have the trajectory of the satellite, and in green, where exactly the occultation was detected. And here the light curve derived from the satellite. Well, this is a proof of concept to try to reply about if we can also detect stellar occultation from James Webb. Yes, we can, but the problem is that these predictions are really challenging due to the chaotic motion of the telescope around the Lagrange 2 point. Well, in spite of that, I applied for time and I obtained time within the Heidi Hamel GTO time to observe one of these stellar occultations from James Webb. This is one prediction. Using, well, ephemeris by NEMA, and also prediction using the tools, the solar tools. And well, this is prediction for the next year, but stay tuned because probably in the next month or weeks there will be news about this project to observe stellar occultations from James Webb. Well, I'm not going to stay here to stop in this slide a lot, because there's another type of stellar occultation like this serendipitous stellar occultation that allow to these are not predicted occultation. These are just observe a star for thousands of hours and observe this occultation produced by really small trans-Neptunian objects that we can't see using direct photometry. There are also another type of occultation that I'm starting to explore, that are occultation of compact radio sources. This is really interesting because with only one core, we can obtain the size of the object. And well, just some examples of the first one was this Bayanor example, but we are starting to use thermal data and occultations to study these objects. This is one of examples, 2007 UK 1 to 6, using a multi-core stellar occultation plus thermal data. We can constrain the thermophysical model and then obtain more information. The same for this object, this Plutino 2003 AZ84. Again, using the result from the occultation, we constrain the thermophysical models and can obtain information about the orientation of the spin axis. That is one of the magnitudes more difficult to be obtained. Again, for Makemake, Chiron, and Cariclo, using ALMA data and information from stellar occultation, we constrain things and we could obtain more information, including, of course, in the thermal emission due to the rings for Cariclo and also the putative rings of Chiron. For Haumea, we did something also similar. We used thermal data and the multi-core stellar occultation, and we reinterpret the thermal emission of Haumea. We see that the contribution of the rings, in this plot you have the contribution of the rings for the different wavelengths with time. Well, the contributions during the Herschel-Spitzer observation was small, but was not negligible. And the nice thing is that this contribution is increasing. Okay, we are here. So the contribution of the thermal flux due to the rings to the total flux is increasing. This means that now we can use James Webb with MIRI at 25 micron to confirm or rule out if the thermal properties that the properties and thermal properties that we obtain from Haumea and the Haumea system are or no real. Well, we also can compare the thermal effective radius and the occultation radius. We have seen that the thermal models tend to underestimate the sizes, around 6% compared to sizes obtained from the occultation. You can see this in this plot. The solid line is the J equal X line, and you see here that the thermal derived radius are underestimating the sizes that we obtain from occultation. This opened the possibility to detect satellites or rings from deviation from the trend. This was done from TC302. We suspect that there is a nearby satellite. And also for Haumea, what possibly is here due to the presence of the satellites and also the rings. So just to conclude, well, we know we have thermal observations for about 180 TNUs and centaurs. We have observed 140 stellar occultations produced by 51 TNUs and centaurs and counting. And we have thermal data for most of these objects. The thermal modeling and the thermal modeling of the stellar occultation, as we have seen, are complementary techniques with important synergies not yet fully explored or exploited. There are a lot of work to do with thermal data and occultation we have. The results of time from the occultations are a key element for the validation and improvement of thermal modeling techniques applied to trans-Neptunian objects and centaurs. And the joint use of both techniques, we have seen, allows obtaining a detailed physical and thermal characterization of selected objects, like diameters, albedo shape, including 3D shape, density, surface properties like thermal inertia, roughness, emissivity, and others. And with this slide, I finish. Thank you very much.
Thank you so much, Dr. Santos-Sanz, for the very interesting talk. We now have time for questions from the audience. You can raise your hand here and I'll call on you, or if you're on YouTube, you can write your message there and I'll read it out to our speaker. Give it. Okay, I guess while people are probably gathering up questions, I have a question regarding something that you said right at the beginning. So you mentioned that you approximate the objects to a spherical shape, right? How accurate is that?
Well, it depends, of course, of the object. Most of TNOs we think are well, we thought because we are seeing more and more Jacobi shapes in the trans-Neptunian belt. But in principle, it's a good approximation. But for objects like, for instance, Haumea, that is very elongated, or others, is not a good approximation. This is for the thermal models, right? That is the easy way to deal with the thermal data. With the thermophysical models, you can use real shapes of the objects. And also there are thermal models. Well, you can also use non-spherical shapes, but are a bit more difficult to program. But yes, usually it works fine, but it depends of the real shape of the object. And yes.
Sorry, so just to be clear, I'll call on you in a second, Felipe. So do you have corrections for objects that you know are like very far from the spherical shape?
What do you mean correction? If we apply the model, then we can correct. No yet. But we have this in this plot that I just put at the end. We have the yes, we have this 6% that this could be, we underestimate by 6%. This, I think, is typically for objects that are not very spherical when we apply this. But okay, this is just a first estimation, right? Because we haven't here many objects, but this could be refined. But of course, it depends of the elongation of the object. This would be larger than this 6% or smaller, the correction.
Okay, thank you. Felipe?
Welcome.
Hi, you listening?
Hi.
Are you listening?
Yes, Felipe. Hi.
Oh, hi, Pablo. Thank
Hello.
you. Very nice talk.
Welcome.
I'm wondering about the ring detections. You showed this plot for AUMIA that the ring is contributing more and more.
Yes, yes, I can.
So
do you think you mean in the thermal,
yeah,
right?
This one.
Yes,
exactly. Do you think we can do the same for the other objects, and can we kind of try to predict rings using this?
Yes, sure. Yes.
So what are the variables that are important on the ring to calculate this contribution?
Well, I don't know if I have understand what are you asking me. But,
I mean, the composition, the size of the grains. What are the variables that can be used to calculate the contribution?
Yes, I think here, well, for AUMIA, we I think was easy because we have everything, but of course you need you need to know the position of the pole, and then derive the position of the rings as seen from Earth. But about the thermal contribution, well, I think you have to assume things because we don't know exactly the composition of the rings for AUMIA nor for Chariklo. But the main point here is where is the spin axis exactly, and this mean where are the rings, if are H on or are pole on. I think this is the main, and from this I think you can assume things and you can derive this kind of plots. And yes, this would be easy to do for centaurs as well. And as you know, the variation in the spin axis for centaurs will be bigger.
So you think that the contribution? So you think the contribution is more due to the surface of the ring that we are seeing, more than to the composition of it?
Yes, definitively. I think the main contribution is due to the surface. Yes.
It doesn't matter much if it's made more
because
crystalline water or other things.
Yes, there's no spectra, so I think it's independent of more or less independent of the composition. Well, it depends of the thermal emission of the material, but I think in this case the main contribution is due to the different surfaces. Yes.
Okay, thank you.
Welcome, Felipe.
We have another question from Julio.
Hi, Julio.
Hi, Pablo.
Hello.
Can you hear me well? Always have problems with the microphone. Okay. So, Pablo, you showed us a slide with occultations involving radio sources. Can you hear me? Okay. Let me try to change my microphone here.
So sorry, I had problems here in my lab with my laptop because. Okay, can you repeat, Julia?
Yes, I think you can hear me better now, probably.
Yes.
Good. Okay, just you showed us a slide about occultations involving radio sources.
Yes.
Yes. Would you?
I can go. Can you see my screen in?
Yes, it's moving. You are
okay.
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 Slides.
It's close to the end of the presentation, I think so. Yes, I did this slide for SKA, because when I studied this thermal emission, we also studied the possibility to observe stellar occultations from produced by a TNO occulting a radio source. But sorry, continue, Julie.
No, okay. I'd like to know a little bit more about this, because you mentioned that with only one cord we could have, I don't know, more essential information about
the size. Well, the point is that we measure the diffraction pattern, as is writing here in the Fraunhofer regime, and then we obtain directly from the observation this Fresnel number that depend of the size, the distance to the object, and the wavelength. We know the distance to the object, we know the wavelength, and we obtain this Fresnel number. So directly from this equation, we can obtain the radius with only one core. So this is nice. And also, well, I don't know exactly how, but I know that people expert in radio from these patterns can obtain also the shape and the presence of satellite, and of course the exact position of the object. This have been done for only for 2 asteroids. At least this is what I know. These 2 papers, Letinen et al. 2016 and Harhu et al. 2018. These are these kind of detections of 2 occultations by 2 asteroids occulting a compact radio source. Never have been done for a trans-Neptunian or a Centaur. So I think it's a nice thing to think about, perhaps to predict and to do in the future. Using SKA or using another radio telescope.
Okay. No, okay. I think, well, okay, it looks pretty interesting. Okay, it's a new domain to me because I do not deal with the radio observations.
Yes. Well, you have you have here the typical diffraction patterns.
Yes.
In your light curve. But if you want more information, please. Write me and I can send you these papers, or also send you this was a chapter for a SKA book, a white book of SKA, and also we talk about TNOs and the possibility to observe radio occultation, but with SK, but it is possible to use another radio telescope if you predict that there will be an occultation visible from this radio telescope. We can try to
yes. The point is that well, first we'll have the LSST that will increase a lot the number of trans-Neptunian objects, and also Gaia that will have I don't know, discover or at least map. I don't know exactly the number, of perhaps 500,000 compact extragalactic sources. And it may be interesting perhaps to have predictions that also consider the
yes. I'm also not an expert in this radio sources catalog, but I think the accuracy is really good. It's close to the millisecond in radio. So yes, if we can access to this radio source catalog, we can start to predict, of course, occultations. And
Yes, the advantage of Gaia, I suppose, is that they may be mainly interested in using a compact sources because of the definition of the referential frame, the reference frame. So in this context, perhaps we can consider that the optical and radio emission centers will basically match to our needs.
Okay. Yes.
Okay, great. But thanks a lot.
Something to explore. Welcome, Julie. Okay.
Thank you. Do we have any more questions? Okay. Thank you, Dr. Pablo, for staying a few minutes longer. We'll wrap this up now. So this presentation will be available on our website and also on Linea's YouTube channel. Thank you, everyone, for attending, and a very special thanks to you, Dr. Santos-Sanz. Everyone, have a great day, stay safe, and I hope to see you all again in our next webinar. Bye-bye.
Thank you very much. Thanks a lot.